This week, we'll be investigating mechanical energy loss in our system. Mechanical loss includes everything that causes our system to lose energy by dissipating it, usually to heat. We'll look at three sources of this loss: Coulomb friction, viscous damping, and deformation. Then we'll talk about how we might account for these sources of loss in our model. Let's start with Coulomb friction. Coulomb friction converts some of the mechanical energy in our system into heat by the act of things rubbing against each other. This is the type of friction that you have probably seen in physics class before and calculated as the force of friction equals mu times Fn. Coulomb friction operates in two different states: static friction and dynamic friction. Static friction operates when things are in contact with each other, but not in motion relative to each other. We already accounted for this type of friction between the wheel and the ramp in the last video when we broke up the normal force into x and y components in order to account for the fact that the wheel is not sliding but rolling down the ramp. But there are more sources of Coulomb friction than just this in our whole system. In particular, there is dynamic Coulomb friction also. In our system, parts rub against each other in the bearings, between the wheels and the axle, inside the motor, and inside the transmission. All of these sources will contribute to cause our system to lose energy through Coulomb friction. Coulomb friction is independent of the velocity of the wheels. In other words, the force of Coulomb friction won't become greater the faster the wheels turn. Next, let's look at viscous damping. Viscous damping includes all of the energy dissipation that occurs due to fluids being displaced as the system moves. For example, as the system moves through the air, it has to push the air out of the way, and this takes energy. There also might be viscous damping in the bearings if they are lubricated with oil. Everything in our system that spins also will be subject to viscous damping as it spins in the air. Now, the force of viscous damping is dependent upon speed. The faster things move, the greater the force. We can calculate the force of viscous damping as force equals B times V. Here, V is the velocity and B is the coefficient of damping. There is at least a third source of energy loss in our system also: deformation. This is the energy loss that occurs because things in our system change shape or deform as they move. Suppose that these wheels have tires on them. That's likely necessary in order to achieve our no-slip condition. When the wheels contact the ground surface, both the tires and the ground will deform, that is, squish, dissipating some of the mechanical energy motion from our system, slowing down the rolling of the wheel. You've probably experienced this source of energy loss before while riding a bicycle. You know that it's harder, that is, requires more force to pedal a bicycle with tires that are flat than to pedal a bicycle with tires that are well inflated. That's because flat tires deform more when they contact the ground, and so they dissipate more energy. Likewise, it's easier to pedal on a surface of hard concrete than to pedal on a soft turf or sand. That's because the soft turf or sand deforms more when it contacts the wheel, and so dissipates more energy. Now, we could model all of these sources of energy loss by adding expressions to the equations we developed last time. But first, I need to point out here that there are two different general approaches that we can take to modeling any system. the analytical approach and the empirical approach. The analytical approach is what we did in the last assignment. We used the laws of physics to come up with equations to create a mathematical model of our system in terms of variables. The empirical approach is different. Here, we perform an experiment on our system and take measurements to make a model in terms of numbers. Each of these approaches has its pros and its cons. The analytical approach gives us more insight into why our system behaves as it does. For example, with an analytical model, we could predict how the system would behave differently if we doubled the wheel radius, or decreased the ramp incline, or used a softer tire. But empirical models tend to be more accurate, because they necessarily include all kinds of small, complicated effects we may not even know how to analytically model. In practice, engineers almost always use a combination of analytical and empirical approaches to model a system. For example, suppose we added in the force of damping to our model analytically. We would still need to get a value for B, the damping coefficient. How could we do that? We could do that by analytically modeling the fluid responsible for the damping, but that's starting to get really complicated. We would probably estimate B by testing the fluid to see how much force it produced for certain values of velocity. So we would have used part analytical and part empirical methods to create our model. One of the challenges you will face as an engineer is knowing when to switch between analytical and empirical methods. Right now, we are recommending that you switch from analytical methods, which you used in the last assignment, to empirical methods, which you are asked to use in this assignment, to add the effects of energy loss to your model. Let's take a look at the assignment. In the assignment, you're asked to find an appropriate stand-in device for the proposed system, and then to determine a method for measuring the loss. For the first question, you have to identify an object that you do have access to that's similar enough to the device that you're trying to design that you can perform an experiment on it in order to estimate the loss that you will have in your actual system that you're designing. Then, in questions 2 and 3, you're trying to determine a method to measure experimentally the loss in the system you identified in step 1. For example, the model that does not include the energy loss predicts that the system will continue to accelerate forever when rolling down a ramp. But we know that the system will not actually continue to accelerate forever when rolling down a ramp. Could you find out a way to measure this difference in system behavior with your stand-in device? If you can measure this difference in behavior, it will allow you to extrapolate the amount of force that comes from all of these sources of energy loss together. Once you've figured out a way to experimentally or empirically measure the effect of all of these sources of energy loss together, can you then explain how you would use that measurement to figure out the additional power required from the motor and the torque required at the wheel to overcome it? That's what question 4 is asking.